Good morning, sir. My name is E. Charan. My roll number is 244G50201, and I am from Triple E Department, Triple E section. And my today's topic is about intersheet grading and how it enhances cable performance. Grading of cables. Grading of cables is nothing but grading of cables refers to the method used to improve the voltage distribution across the insulation of cable to enhance its efficiency and performance. The main goal of grading is to reduce the maximum electrical stress, thereby increase the cable's lifespan and reliability. Grading improves the efficiency and high voltage cables by reducing insulation breakdown risk and optimizes the performance. Yeah, this is about the grading of cables, and this uh, grading of cables is there are two types of grading is capacitance grading and industrial grading. First one is capacitance grading. The insulation is made up of different materials with varying permittivities, dielectric constants, and to create uniform voltage gradient by reducing maximum electrical stress. That is the G maximum. We look at the G maximum grading of cables. The second one is intersheet grading, used to multiply concentric layers of insulation of same relative permittivity with intermediate conducting layers. Intersheet grading at 2 points. Next, we can go to grading of cables. Intersheet grading consider a single core cable of core radius smaller and the outer radius of insulation is capital R. With insulation permittivity, we can consider as the potential at surface of consider is V1 and potential at outer surface we can consider as V2. This is about the diagram for the single core cable. This is the radius of inner sheath of inner conductor radius, and this is the outer conductor radius capital R, and this is the inner sheet insulation V1 and potential V2, and we can derivate the in single core cable at any distance x from the center of the cable. The electrical field intensity is given by capital E x is equals to q by 2 pi epsilon r, and we can consider as equation 1, and E max is equals to q by 2 pi epsilon r, that is we can consider as equation 2. The potential difference across insulation is given by V1 minus V2. We can consider the potential difference across insulation we can consider as V1 minus V2, that is equals to minus the equation for the potential difference minus integral of capital R to small r ex dx is equals to minus integral of capital R to small r q divided by 2 pi epsilon x. D of x is equals to q by 2 pi epsilon natural log of capital R by small r. That is the final equation for potential difference across the insulation. That is the equation 3. And from equation 2 and 3 we can consider as E mass is equals to V1 minus V2 divided by uh, small r into natural log of capital R by small r. Again, we can consider as unit is kilowatt per centimeter, and we can write as equation number 4. And from equation 4 is evident that the maximum stress can be effectively controlled by adjusting the potential difference between 2 points. This can be activated by incorporating intersheets as shown in figure 20. This is the single core cable for intersheet grading, and this is the transformer. This is the transformer windings, and this is the slots. Sorry, uh, dampings for single core cable. This is the conductor of single core conductor, and this is the layers for the insulation, and this is the outer sheath, and we can consider each layer of insulation, that is we can consider epsilon, and let we consider smaller one by mm, r1 by smaller is equals to r2 by r1 is equals to capital R by r2, that is constant k. This is the equation number 5, and let me consider r1 by smaller is equals to r2 by r1, and this is equals to capital R by R2 is equals to constant k. Potential gradient at the radius r, that is ER maximum is equals to small g r maximum is equals to v minus v1 by r into natural log of r1 by smaller, and we can consider as smaller equals to r1 r2, and we can consider we can we can write this equation 6 7 8 we can add, you can add v this v place to v1 and v2, and we can consider minus 0 is equals to the potential difference potential gradient at radius r2. For effective utilization of insulation, the maximum stress given by equation 6 7 and 8 must be equal to this capital E max maximum is equals to small g maximum is equals to v1 minus v minus v1 by r into natural log of v1 by r, that is equals to v1 minus v2 by r1 into natural log of r2 by r1 is equals to v2 by r2 natural log of r by r2, that is equation number 9, and we can consider v minus v1 by r into natural log of constant k is equals to v1 minus v2, that is divided by r1 into natural log of k is equals to v2 by r2 into natural log of k, that is equation number 10, and we can finally conclude the v1 minus v1 v minus v1 by smaller is equals to v1 minus v2 divided by r1 is equals to v2 by r2, that is equation number 11, and we can consider the final equation v2 is equals to v1 into k divided by k plus 1, that is equation number 13. From equation 11 we can write as v1 minus v1 divided by small r is equals to v1 minus v2 by small r1, and since v1 is equals to v into k into 1 plus k by 1 plus k plus k square, that is equation number 15, and the gradient of cables of E maximum, that is called G max is equals to v minus v1 by r into natural log of r1 by r, that is equals to v minus v into k into 1 plus k divided by 1 plus k square by r into natural log of k, that is equation we can consider as 16, and we can write as last equation since E maximum is equals to small g max is equals to v by r into natural log of k, that into 1 by 1 plus k square, that is equation number 17. The equation number 17 represents the maximum potential gradient or electrical stress with intersheets. Let we suppose the cable is not intersheathed, the maximum electrical stress or potential gradient, say maximum E max or G max for the same operating voltage capital V is given by E max E dot maximum is equals to G maximum is equals to, we can consider as V by 3 into R into natural log of K, that is equation number 18. From equation this 2 17 and 18 we can consider as E max divided by E dot E bar max or E bar max, that is equals to 3 by 1 plus k square, that is we can consider as final equation that is E max is equals to 3 by 1 plus k square, that is into E bar max. We can consider since the term 1 plus k square is always greater than the 3 3 into 3 into E capital E max maximum, is less than E dash maximum, that is maximum electrical stress of intersheated cable is reduced. For operating voltage, V of cable is given by V equals to E max into R into natural log of R1 by R plus R1 into natural log of R2 by R1 plus R2 by natural log of capital R by R2. That is equation number 21, and equation number 22 is we can consider in the in this uh, area we can substitute the equation R plus R1 plus R2, and finally we can conclude these for the same E maximum. The operating voltage V without intersheath is given by V bar is equals to E maximum into R into natural log of R divided by R, capital R divided by small r is equals to E max is equals to E max into 3 into R into natural log of K. From equation to 22 and 23, it evident that the operating the greater than the case of intersheath cable for the same as side cable, single core cable. And this is the information about intersheath gradient and how it enhances cable performance. And thank you, sir.